I'm sharing the screen. It should be second screen, I guess. Share. And then it's this one. Okay. AI, hardware, energy efficiency. I mean, always challenge. So what's your current state of mind on this question?
How do you mean?
So people are saying that AI is totally energy inefficient. Why? I mean, what are the reasons?
How to divide? Oh, it's hard for a computer to make division and multiplication. So if we had something that was better at that, it could be fine and great if it could do that. And well, it takes a lot of crunching numbers to get our answer to do that. And we often have to do it multiple times.
Yeah, yeah. In one class from now, so I want to trace the backprop algorithm. So exactly well, I am pretty sure that you know the backprop, but I want to go to the math of it. So that you see the kind of where the computations happen, and so to say, mathematical reason for this amount of computations which are taken. Yes. All right. So let me just find out if I zoom. Let me see. Oh, I know. Raise your hand. Yes, I mean, you on Zoom, you're free to unmute yourself and speak up if you want to say something. Because I normally I don't see the chat window. But yes, and what are the trends then to increase or improve the energy efficiency? Of computations in the AI context. I just want to check. I mean, what I mean your current state of knowledge is. Yeah, but okay, yes, Jose, you wanted.
Yeah, I just wanted to mention that they are creating specific hardware for inferencing neural networks, they call them accelerators or AI ASICs, and also there is like a whole field in neuromorphic computing that actually we have another subject about it, how to make spiking neural networks that are neural networks more close to the biological ones, and they are much more efficient than the regular ones.
Exactly. So, and it is there I'm heading to as well. And we will not go into the neuromorphic computing part, but this is the trend to search for alternative computing methods that increase the energy efficiency, the number of useful computations per unit of energy. So yeah, but again, so we have the mainstream computing architecture, so von Neumann machines, and we have and here we have a couple of bottlenecks. But before talking about bottlenecks, I mean, these architectures are extremely optimized to do exact computations. So computations that require high precision. And as such, they achieve their purpose. But when using in the machine learning or AI context, it apparently becomes very inefficient in terms of the number of compute or the amount of compute we need to achieve certain functionality. Moreover, I mean, as Jose also mentioned, biological organisms, so they require orders of magnitude less energy to be trained for very complicated or sophisticated tasks. I mentioned, I don't remember if I mentioned it during the first class, but so part of my collaboration is with a group of biological behaviorists who studied honeybees. And so honeybees can master such concepts, abstract concepts, to the left, to the right, above, below, only in 30 to 40 trials. And and then perform very well on test runs. And so modern neural networks, so they require substantially more data to be trained on these tasks. And special architectural decisions. So there is still a quest on how to optimize algorithms and what would be the computational principles suitable for AI applications. But now let's talk about bottlenecks. And when talking about bottlenecks, so I want to quickly arrive to the need for alternative hardware architectures and basically talk about two main threads in this domain. Two things that limit the energy efficiency in modern computers. First is the memory CPU wall. So you always need to shuffle data between memory and the processor, and this becomes a bottleneck. And secondly, the nature of precise communication. So you in modern architectures, you need to over provision the chips so that they perform sufficiently well with respect to accuracy of floating point operations. Again, and this is due to physical properties of the hardware and electromagnetic emissions on the chip. So and due to the minimization of the transistors, so you try to pack more transistors on the chip. So I mean, with the goal to compute faster, but at the same time, you need to increase the voltage supply so that the current basically reaches all the transistors on the chip. Again, so on a hand waving level. And at the end, to achieve desired precise performance, so that essentially, I mean, when you add 2 and 2, it equals 4. So the current technology supplies substantially more energy that is in principle needed for achieving same results. But again, this is done for reliability purposes. So what happened, and that is what is displayed here on this graph. So you try to achieve more stable behavior from all the computational elements, transistors on the chip, and you do this by increasing the voltage supply. But that means that your energy efficiency in terms of number of operations you perform per watt of energy, it decreases over here. So basically, all the optimization techniques, they concern moving this, increasing the efficiency somehow. But again, so the current computational computing technology, it has this sweet spot, so to say, beyond which the computations become unreliable. So you cannot simply continuously reduce the energy supplied to a chip, because after a certain threshold, your transistors become, you will see lots of bit errors, so bit flips over here. So you end up in this region. So the takeout from this long passage is that there are two bottlenecks. One is the inherent properties of the current computing technology. So that's which is optimized for precise operations. So you want if you want to achieve reliability, you need to you cannot or there is a limit until which you can reduce the energy supply, because beyond that, so your chip starts to produce errors. And the famous or infamous memory wall. So they need, yes. Yes, exactly. Yeah. So I mean the yes. Mm-hmm. So two approaches, two mainstream approaches connected to kind of counteract this challenge. Well, I'm not talking here about accelerators of this of the operations specific to neural networks, which are mainly vector matrix multiplication or matrix multiplications. So these are done by parallel architectures. So which lead to increasing speed, but again, so not directly lead to reduced energy consumption, because due to the amount of computations that are needed to be done anyways to train models. But talking about alternative ways, so there are two mainstream approaches. There are several, but two of particular interest. First is so-called in-memory computing devices. So when you and the overarching idea is that the memory is not used only for storage, but also to perform computations. And so this type of hardware solutions in the AI machine learning context, they can be really used for speeding up search whenever you come to this task. So during pattern recognition. So even when we talk about KNN. So such memories, such architectures can help inefficiently implementing the search. And secondly, second approach currently maybe even dominating in the alternative hardware solutions is the solution based on utilization of spiking neurons. So those are neural networks that essentially emulate the biological neurons. Yes.
You said before that you use the memory for both storage and computation. we usually have like a RAM and normal storage.
Yeah.
You mean that you combine it?
So you enhance the memory block with computations. I have an example that makes it a little bit. So do you have anything in Zoom? Then I mute you for a moment. Again, the main difference, I guess some of you have had a course with Fredrik Sandin on spiking neural networks, right? Who didn't? Huh? All of you had. No, no, you don't. Okay. But this is a type of neural networks. So where you have a computational element called a neuron, but compare it to artificial neural networks, which are successors of perceptron. So which are based on back propagation training algorithm. These neural networks they use principles of biological neurons. So Hebbian rule basically to train. And but before all, as I said, so they are emulators of activities researchers observed in biological neurons. So basically, a neuron has an excitation level when a voltage or an input, which is really a voltage, reaches a certain threshold, then a neuron starts to emit spikes. So you design a network of such neurons which exchange spikes, and then you load it with learning rules so that the spikes are somehow becomes correlated to achieve desired output. Again, on a very high level manner, on a very high level description. But overall, so in AI applications, one has to, if you think about improving the energy efficiency, the first thing you probably are interested in how to change the algorithmic principle so that to reflect the imprecise nature of computations that I observed in brains. And this principle is also known since a long time ago. So before our digital technology, there was a period where researchers came up with analogical computers and principles of imprecise computing, so or stochastic computing. So where computations were done observing the patterns in the input signal and so basically stochastic behavior of input signals. And as such, so what we want using these principles is that we can work in this under voltage regime. So we want to make algorithms that are robust to noise, to bit flips, and so that is where we are heading to. Talking about so just to summarize, I talked about two approaches towards alternative way of implementing computing in hardware tailored to AI applications. One which is based on in-memory computing, so you load memory with some extra computations. And the second one is to try to mimic nature. And so since we have evidences of very energy or power efficient operations observed in biological organisms while learning, and we are talking about utilization of spiking neural networks. And the third point I mentioned is the change of computing paradigm. So and this is applicable to both hardware directions. So the computing paradigm should allow for imprecise computations, so that in either way, whether you use spiking based hardware or in-memory based computing, you can do it at as low energy levels as possible. So and as such tolerate errors. So what is again just on to overview the state of the art? The first in the trend in memory computing is also focusing on using special materials that can be used instead of transistors or and these materials are these devices are called memristive devices. So they're based on materials that exhibit both the conductive and resistance properties depending on the voltage that you supply. Based on such materials, so you can build array-like architectures where these elements are stacked on a 3D volume or 2D wafer. And computations in this case would be done by, first of all, loading this architecture with the patterns that you want to recognize, and then supplying and building the interfaces for hardware-friendly queries. So what is meant here is that you tailor the design of your hardware to the specific computations. So here I reference this paper that appeared a couple of this particular is from 2020, but there were several others after that in Nature Electronics describing the constant time search or an architecture for constant time search. So the idea was here that they built an architecture for one-shot dot product computation, so similarity-based computation. So they stored patterns in this case in rows of the chip, and then the query was converted to kind of vertical level currents that's basically in one shot resulted in activation of pattern which is most similar to the stored one. So what? But this type of architecture, so it doesn't accept any kind of pattern. So we again. We are talking about such data representation that allows for errors in it, and it was specifically tailored to that to the representations using hyperdimensional vectors. As for the spiking hardware, so here we have several alternatives. So this chip producers. The one I'm working with by my PhD students is a chip from Intel. So it's an experimental chip called Loihi. And essentially, so it's a digital architecture that implements spiking processes. So it's, I mean, you can think of it as a silicon implementation of neurons and a message passing scheme on the chip to emulate spikes. And it is fully programmable so that you can implement learning on it. So, and the programming is done using a specially designed Python-based framework, which is called Lava. So I'm telling you this again that maybe you could be interested in exploring these alternatives for machine learning tasks and these alternative learning mechanisms. In this case, so you should know that there are well-developed frameworks that are tailored for specific hardware. So what is happening here? So what again can you do very efficiently? Again, so concerning classical machine learning applications, you can do again a very fast similarity-based search. So you and this is achieved by kind of very by highly parallelized search. So you basically encode your patterns into synaptic connections, and in one shot you see activations of a certain pattern. And since the chip is energy efficient by the design, so I mean it operates in the under voltage level. So this similarity search based on imprecise data representation, which again can be achieved with high-dimensional vectors, as I introduced last time. So you achieve high accuracy of the search as well as energy efficiency. So one of the if you would ask me, so where it all goes, I think it will. I mean, in the future we will see a hybrid architecture. So we will see definitely in-memory computing as part of the AI hardware, as well as computations based on spikes. But there should be something common computing denominator, so to say. And in this case, these methods that I started to present you last time are proposed to be this kind of common denominator. So let me see. So let us spend now some time before the break talking. So we come back to the algorithmic domain and see some examples how hyperdimensional computing can be useful tool in this context. So recall from yesterday that the main property here is the noise resistance. So because all our computations are done based on the assessment of similarity between constructs using vector algebra. We, by definition, become very tolerant to noise. And now I want you to show two aspects in the learning pipeline, both supervised and unsupervised learning pipeline, where these high-dimensional representations make sense and lead to improvements. So here we see a kind of generalized pipeline. So if you look at the upper part of this slide, so then we see, well, we have input data somehow converted to feature vectors, and then you have several algorithms at your possession, depending on the task you're dealing with, which help to, for example, build a classifier or a regressor or a visualizer of your data, as with self-organizing maps that we will look next time. How we can use these high-dimensional vectors and this imprecise computing in this context. So there are at least two main trends here. First, you want to use it, or you can use it in the data encoding path of the pipeline. So basically, what I mean here is that instead of kind of supplying the feature vectors in the kind of raw unprocessed format, you first convert them into high-dimensional representation. So here, VSA stands for is a synonym synonymous to hyperdimensional computing. It stands for vector symbolic architectures, which reflect the symbolic nature of the algebra. And then what you can do, you can also, I mean, once you've done it, so you've done the transformation, so you can use these representations with classical machine learning algorithms. And as I mentioned you last time, this process is explicit implementation of the kernel transformation. So you potentially you improve this separability of data. But then, as such, you can, as I said, you can enter it into classical algorithms. And as the next step, so you can also tailor the algorithms. So you can modify the algorithms to work with this type of data. And as such, so the entire pipeline becomes implementable in this kind of imprecise manner, still leading to good accuracies.
Does hyperdimensional computing replace some, or when you go from VSA encoding to features, do you use the hyperdimensional to replace some?
It is like this. So, yes and no. You can use hyperdimensional computing as a tool to encode data structures in a format that it is acceptable compatible to existing classical algorithms. For example, self-organized maps. So without any modification. So self-organized maps will work as we will as is and as we will look at next time. Or you can maybe I can jump over to the display. So you can do this in representation, and then you can try as I said, input to different existing classifiers, and you can observe substantial speed up. So yeah, I mean, for the details, I can refer to this particular application, so which shows the details of the experiment. But the point is that what you achieve with this transformation is two things. First of all, you kind of make data, you modify data properties, hopefully in a positive direction, so that you would need less data to achieve same accuracy. So but also you can in many cases you can achieve compression of data. So in specific use cases. So one of such use cases which are most intuitive, maybe, is this representation of n-gram statistics. So that you will be working with in lab 3. So representation of texts. So so for n-gram statistics, the classical n-gram statistics, so you should keep counters for all possible combinations. And the number of such combinations, it grows exponentially with the size of the n-gram that you have. However, if you employ encoding, so you basically rely on the properties of algebra or mathematical properties of high-dimensional spaces, and you encode sequences using permutations and sets of n-grams in a sentence in a superposition. So just by adding it, so basically you do all the operation on the fixed size representation. So you can achieve substantial gain in memory while having similar oh, where is this graph? Here. Comparable accuracies. So this table, what you should see, so this the first column is a traditional representation, which is very memory inefficient, versus representations using high-dimensional vectors. So here you see the factor for memory reduction and test speed up, while again, so here is the accuracy for both methods. So for some it is a little bit low, but still kind of comparable given the speed up and the memory consumption gains you observe. So, and this brings me to a kind of one message that I want to deliver before the break. In machine learning, accuracy and resource consumption should be considered jointly for a specific use case. So it is not always that we should aim for kind of best possible accuracy. Sometimes you can sacrifice your accuracy in favor of simpler operations. So again, an example would be these wearable devices. So and accuracy of determining, I don't know, heart attack. So if your difference is within, say, 10%, or okay, I don't say 10, but is lower than the best possible performance with the most sophisticated classifier, but it is determined faster, so you allow for some false negatives, then it is still acceptable because you can implement it. You can implement this kind of check locally and test possible errors, for example, on the server. Yes. So let's take a break, 5 minutes, and we'll talk about how to use it in other contexts. And I will share. So now you should see my screen again. Again, so now I have different kind of slides, again, demonstrating different aspects. I mean, I could think about, say, giving more classes on that, but say I rather prefer to show you some snapshots on where it is applicable and what do we gain by, as I said, computer science, but algorithmic optimization of AI. So you need to, if you want to get substantial improvement in the performance, most likely you or I think you need to reconsider computational principles. And in particular, this high-dimensional computing is one of such attempts, and promising in many respects. For example, what you can do, maybe at least it will stick on into your minds when you think about machine learning AI problems. Last year work published on NeurIPS, so one of the top conferences in neural networks context, which suggested an algorithmic way for parallel training of a neural network architecture. So, what do I mean by this? So here we talk about, I mean, it's exemplified on the case of image recognition and training a transformer architecture. So you supply images and a text, and what is done here is that you train in a single run in a single run. You train on several different categories simultaneously. And how is it achieved? Again, a main principle. So this key, I mean, what is written here? Well, first of all, on the left, the input on the left, whether it is image or text, it is transformed into vector. So it is vectorized somehow. And the key on the right is a vector of the same dimensionality, randomly generated. So to indicate that so this particular input belongs to a certain category, dog. So you kind of embed the label into what you into the actual input that you try to train the network on. And then you can have these different channels. What you do, what you actually input to the network, you input a superposition of different categories, and that is done by first multiplying. But again, well, I'm telling you in the true computing terms. So it's position, it's element-wise multiplication or Hadamard product. So you of two vectors. So element by element. So you just multiply them. With randomly generated vectors of same dimensionality as inputs, and then you just again add them. So it's position by position, and the resulting vector it's not somehow due to the properties of this high dimensional spaces. So the resulting vector can represents a set of these channels collectively. So in a single representation, you have different channels. Yes.
So is it correct if I look at it like if we have three signals or my voice, it consists of like 5 to 10 different signals that make my word. It's the same thing, just we combine different signals. That's
yes. And talking about signals, so now I will now jump onto signals. Maybe this will make further connection to what you mean. And then so you use this kind of compressed form, so a single vector, and you train a network on these representations. So you already kind of you save data or you improve computations already on this level. But then if you want to decode it, so let me see. So somebody, would you mind to maximize the window? Yeah, I would, of course. Sure. Sorry. Oops. Yes. So if you want to decode it later on, so you take the output of the network and then you apply the inverse operation. So if here you kind of multiply, so then so you need to extract the result as well. And then you kind of make it as part of the traditional backprop pipeline. And so you get a single neural network that to which you can supply collectively compressed or packaged input, and then successfully kind of demultiplex it at the end. Quite interesting. So, but again, so to know more details, so look at this MIMO-nets. I think it's an interesting concept in itself. Talking about this, the signals, I have my own endeavor, so to say, into this area. It all started with a work. Let me see. Let me maximize it again. Of my colleagues in Germany who worked with the time series analysis, and apparently there is a technique. So at the end, you want to classify signals. So each signal is a time series, so discretized and quantized signal, and you want to. Now I see even charts. I don't know what happened now, but the screen is black. Is it black for all?
At least for me it is. I don't know. Yeah, other people are saying also yes.
Well, let me reshare it. What about it? No.
Now we can see it. Thank you.
Yeah, but nevertheless, so we are talking about signal classification task, and one of the approaches. Well, there are different ways. You can use this plain neural architectures, recurrent neural architectures. We will be talking about them on the last class. To train a network, to kind of the idea is that you unroll, you input to the network the raw signal, and somehow you unroll it in time, and then you try to figure out. I mean, well, you train the network in a backprop manner to classify into n categories. One other approach is to extract descriptors. So you use some convolutional network to extract descriptors of a signal at given point at certain points, and then so you now you have n vectors, so produced by a neural network, which then you can aggregate, just add together, so vector summation, and then you get an embedding for the time series, which you can use to build final leg classifier. And so this technique is called mini rocket. So it is based on the extraction of this descriptors. What we have considered, and maybe that, if I understood it correctly, maybe that's what you meant as a use case, is a case of multivariate signal processing. So you have n sources of signals, and you want to build a classifier based on them. But collectively, they constitute one or another category. And there are different ways to deal with this situation again. So yeah, I mean, what you can do, for example, and by the way, so that's what I'm saying. It has a really practical implication. So whenever you want to kind of combine different inputs and input it to a neural network or to any classifier, first thing you can imagine is to concatenate all these signals. In this case, you don't lose information, but of course the drawback is that you increase memory consumption. So the larger is your input vector, so the more complex is the architecture of the downstream classifier. And then obviously it becomes quite prohibitive for cases when you have many channels. So some standard data sets, for example, have cases with 100 channels. And if, for example, an embedding of a single channel is maybe 1,000 bits. No, 1,000 dimensional real valued vector. So then basically when you stack 100 of these embeddings, then it becomes rather large inputs. again, so in the same manner as the original embedding was produced, you can superimpose them, but so you add together. And that is again, it's nothing very special to high dimensional computing. It's one of the standard steps in aggregating data. So you would simply add it. For example, in attention-based networks, so you have this weighted addition of the attention vectors that a given input hit. So that's but the problem is, and now that's what where this math of high-dimensional vector spaces come into play. When you do addition, and normally when you do addition, you also need to do some processing of the magnitudes of the vector. So normally you maybe apply some. But even if you don't do any processing, sorry for messing up. The more channels you add, so to say, the more vectors you add into superposition, so the more information you lose about each individual input. So say, and this is because of, again, a very simple principle, which is valid even for all machine learning algorithms. Not all variables are equally significant for solving a specific task. So that's why we do dimensionality reduction. So the same principle is here. So in a multivariate processing, so not all channels are significant for classification, but when added together, so they add to noise of significant representation. So it's harder, and this is this noise is observable again if you analyze the similarity properties of this resulting vectors for different classes. So they become virtually indistinguishable. So I mean, all classes look similar to all classes. Yes. And here is exactly when we can do improvements using the using other operations, other vector operations and their properties in high dimensional spaces. So, for example, again, similar to what I presented previously, you can assign individual keys to randomly generated patterns of the same dimensionality to each embedding over here. What do you achieve by this? Since you an add you add it in a multiplicative manner, and when you do that, since you multiply with randomly generated sequences here, you improve distinguishability between channels. So because this is a property of multiplication in high dimensional space. But still, I mean, it doesn't. It does solve a problem of distinguishability. So you can, in principle, looking at the resulting vector that leads to a specific classification, you can say, okay, which channels contributed to. Yes.
Could this also solve like security concerns with AI? Like if I have medical information that I want to put on my AI.
We are, yes, that's a great question and reflection. Absolutely. And I don't have the slide, but I can point you at least to one video recording on my webinars that deals with it. Because obviously, so you can assign a random key to that the input becomes unintelligible, basically. So and this is called data obfuscation. So you obfuscate the data, but still the important thing is that you preserve, again, so the similarity pattern. So you obfuscate the data, but with respect from the point of view of neural network or any other machine learning algorithm, it is still same data because it is based on kind of drawing a border with respect to some similarity measure. So yes. On the other hand, again, so you touched a problem which is more complex than that, because doing this thing, assigning a key, it does obfuscate the data, but it doesn't encrypt it. So and so there is quite some difference. So the people are working on techniques where you can encrypt the data and still being able to learn. So that's the type of functionality is called homomorphic encryption. But I mean, this is very challenging to do processing on encrypted data for a good reason. Again, by the reasons, fundamental limitations of imposed by mathematics in the high-dimensional space and the way how encryption is done, which require exact operations so that you can backtrack. But again, so I drifted away. The answer is yes, it is useful in the context of secure AI operations. And currently, I have one new PhD student actually who finished this program last year, Tim Ufer, who is looking exactly into these issues. So, and we have I have even one master thesis looking into this. So if you are interested in this domain, so we have the dedicated project for that. Yes, but what I want to show with this is that just blind summation again is not very good. So and this is again connected to introducing noise when from insignificant representations for solving a specific classification task. And what we did last year, we designed a backprop architecture where the trainable part are not the per position weights, because I mean the entire vector here it has direct translation to activation of individual neurons, basically. So you can represent all the operations that I presented yesterday in the context of high-dimensional vector algebra as a neural network, as a perceptron, basically. But here we designed a neural network which is based on the aggregates. So more or less, I mean, you can think of it as a you train the entire activation of the you weight the activation of the entire hidden layer, roughly speaking. But otherwise, it's pretty much standard backprop architecture with some modifications. But I just want to show you some results. So what, for example, so you have n channels. So from 1 to 1,000. And only one channel is has true data, and that is relevant for classification. All others are not. So we just generate noisy channel and data series. If you, well, there are substantial difficulties to train classical algorithms based on, I mean, in the settings. So in this way, so I mean, when you kind of look at it from the vector algebra perspective and try to train so which vectors are not significant. So you train the weights of this entire representations which contribute to the classification. Then it becomes more tractable, basically. So and rather very quickly the network understand that which channels are not significant at all, independently on the number of channels. Talking about this, another interesting thing, let me see if I find it. Where is it? Let me see. Here. I will not. Here, very interesting, I think. A different context. Oops. No. Multitask learning. So again, I'm sorry for I'm jumping from topic to topic, but again, in the area of AI, so there are more sophisticated setups where deep learning faces challenges, and one of such setups is connected to multitask learning. So you have different tasks. Say task one is MNIST, just handwritten digits, black and white. Another task, another task is the same MNIST but perturb it. So you basically permute the pixels. So they, and obviously they. If you train the network on plain MNIST and you supply permuted MNIST, so then it will produce garbage, right? Or so you can think of it, for example, you take this cipher data set, so you train on certain categories. So you can split it, split available categories into subcategories, and first train a network on one set of categories, and then you kind of want to train it on the second category. So, and here we have this phenomena of catastrophic forgetting. So what do I mean? So I mean, so you in this setting you have a single neural network, as would be the case for kind of modeling biological intelligence. We do have a single neural network, and we are flexible to learn multiple tasks and retrieve multiple, and kind of operate with multiple contexts almost simultaneously. So this is a similar setting. So you have a backprop deep learning network here, and you supply, but you want to train it on multiple tasks. If you don't do anything, and you train the network on a single task until it converges, and then you forget the samples of the first task, you start to keep on training on the second task, until convergence on the second task. And then you show the examples from the first batch of tasks, from the task from the first batch. Then you see that the network performs extremely poorly. So it forgets totally about the first task. Obviously, I mean, that's kind of normal. And what you, so if you read again this NeurIPS paper from, again, my colleagues from UC Berkeley, so they are from Neuroscience Institute for Theoretical Neurosciences, and look at some alternative learning modes. that resemble better biological learning. So they came up with an interesting scheme. So if first of all, they introduce a context. So basically, each task is a new context, and the context is encoded in a randomly generated permutation matrix for each hidden layer. So a hidden layer is a matrix connection, right? So on top of it, so you can really place the connections differently, but you rewire connections. And this rewiring is specified by a matrix, permutation matrix, a context matrix. So this matrix is again is a random permutation for each task. And what they did is that okay, so you train on a single task, so for initial initialization of neural weights, and then before you start to supply examples for the second task, you apply the context matrix for this task. So you rewire the network and keep on training. Then for each next task, you again, but then, so if you want to test the network for the first task, so you need to kind of unroll it back. So and this is done again using operations which are very similar to what I presented to you in the vector context. And as a result, so that is if you yeah. So this so the green line is a catastrophic forgetting. So basically it doesn't remember anything. So this is multi-hat. So you have like different hats for different tasks. And this one is a single neural network applying this context matrix and a test on the kind of first task after training on several tasks in a row. And again, so there is a natural explanation. I mean, when neural network is trained, not all, yes.
My question is going to, I need to supply the permutation matrix for each desired task. So if I don't know what task it's supposed to do.
Correct question. I mean, it goes a little bit beyond the practical case. I mean, in this case, you presume that you know the context. So, and normally you have a kind of, so how to characterize a context. So this is a different thing. So, but in the case of kind of intelligent agents, so you normally have some clues that can characterize the context. So it's not that, I mean, in the machine learning context, you always deal with well-defined tasks. So you have only a single task. So this is a setting more in a general AI context. And in general AI context, you normally can characterize in which context you try to solve a problem. And as such, it is presumed that you can, knowing the context, you can find the appropriate matrix. But it's kind of interesting stuff. So it's, I hope you at least get some feeling of cool applications. And there are really interesting other applications. So maybe, now I cannot let it be to advertise again, but this VSA online that I lead since 2020. All these talks, you can have a look. The relationship to so this Maimonides, if you want to have a good kind of introduction, so a more detailed introduction, so it is here. Even talks related to modeling of sleep. Some neuroscience related talks. So you can find many things here. Those of you again interested in more computer science questions, so there are data structures which are called sketches. So you have a data structure that collectively describe a complex data in a vector format. So that's again very related to high dimensional representation. So plenty of interesting stuff. If you would browse, so I can link it from Canvas if you're interested. Yes, okay, thanks for this time. So if you have any questions, you're always welcome. Next time we continue with something more conventional, so it's self-organized maps and the backdrop.
Thank you. Evgeny, can you hear me?
Yes, I can hear you.
Could it be possible to upload these slides to Canvas? Once I'm going to finish it today.
Yes, I will do a compilation of slides. Yes, absolutely. Yes, I will. And
Yeah, thank you.
you will see it on Canvas.
Yeah, and could it be possible, I don't know, to reach out to you, or maybe if you could share in an email, because you mentioned briefly like master thesis ideas related to this.
Yes. So what kind of information do you need? I mean, or maybe, I mean, if you have some, you can write a message to me so that I can reply to you.
Yeah, okay. Thank you.
Yeah.
Have a nice day, bye.
Yeah, you too. Bye. Jag tänkte bara slå. Nej, men det är lugnt. Kom. Jag bara slår av Zoom.